Welcome to the third lecture on our topic, machine learning, ladies and gentlemen. Previously on our lecture, we've defined J of theta to be that, and basically that's the average, which is the half of the square of the difference between the predicted price and the actual price, taking into consideration the number of training examples, which is M training examples. So basically, in our lecture today, I want us to look at the concept of the gradient descent. All right. In the concept of gradient descent, we want to minimize this quantity J of theta as a function of our parameters, right? Our parameter vector. Now, let us focus on a different algorithm to minimize J of theta, all right, called the gradient descent. All right. Basically, what we'll do is that we will basically take a look at the search algorithm that does that. Right. Let's look at the gradient descent as the first algorithm to minimize J of theta. Okay, for the gradient descent, the basic idea is that we start at some value of our parameter vector theta, all right? So the basic idea is that we will start so the basic idea is that we will start at some value of our parameter vector theta. So we're going to start at some value of our parameter vector theta, all right? And basically, gradient descent depends on where you start, where you initially choose your starting point, all right? So it depends on where the thetas are. So basically, the gradient descent depends on where the thetas are initialized. All right. Say, for instance, we initialize the parameter vector to a vector of all zeros, right? For instance, we choose theta to be the vector of all zeros. Then what we'll do is that we'll keep changing the parameter vector to reduce J of theta, right? So here we will keep changing the parameter vector theta to reduce J of theta. So that's the basic idea. All right. That's our basic idea. All right. Say for instance, you are aiming to the scale where you had a hill. If you have a hill and you start somewhere in the hill and take small steps going vertically downwards, you end up getting at the bottom of the hill, right? Depending on how many steps you take or which direction you take. Right? You end up being at the bottom of the hill. So basically at the local minimum. That's what we actually want to achieve. All right. I just thought of making a little example. I just want to make a little example regarding gradient descent. All right, so this is the idea, right? Consider this, I just picked up this action. Consider this egg container as the surface as the j of theta. So the surface is gonna be the j of theta. All right, so it's gonna be the j of theta. So imagine we started at a point there. Okay, imagine we start at a point there, and then we take this small step down, keep going down, keep going down. Imagine we're going vertically down, we're not changing any direction, until we get to a point there. All right, so when we are at that point there, all right, we want to get to this local minimum. This is where we want to get, because this is the minimum. All right, this is the ground. All right, this is the minimum. This is what we want to get. But now, say for instance, we had to start there. All right, we had initialized our vector parameter to be at that particular value there. All right, and then we keep taking these small steps. We're going down the hill, we're going down the hill. But unfortunately, we are not there at the bottom yet at this stage. So if we are at the point where it is not a minimum, then what we do is that we say, okay, I'm at this point. Now, I look around 360 degrees around me. I say, okay, where can in which direction must I take in order for me to be able to get to the minimum? And so that's that. So I keep taking now vertically steps. I keep taking steps vertically straight down until I get to the local minimum. So imagine if you're on top of the hill and basically you want to get to the bottom of the hill, and those are the steps that you're going to take. So basically that's the whole idea regarding the gradient descent, all right, algorithm, right? Because we want to take steps that will get us to the bottom of the, that is to the local minimum as efficient as possible. All right. Basically, the idea of gradient descent is that we repeatedly take steps in the direction of the gradient descent. Okay, let's just write that down. We repeatedly take steps in the direction of the steepest descent. Okay, so we repeatedly take steps in the direction of the steepest descent. Here is an algorithm for the gradient steepest descent. All right. So an algorithm goes theta I is equal to theta I minus alpha, the partial derivative with respect to theta I j theta. All right. So basically, that's the basic algorithm. All right. So that's the algorithm that governs the gradient steepest descent. Right. Basically, take note of this notation. What this notation means, say, B column is equal to C. So what that means, it means that my expression on the right hand side, which is C, right? It means that C constantly overrides the value of B, all right? Constantly overrides the value of B. This is what it means. The new value of C overrides the new value of B. The new value of C overrides the new value of C. Unlike if I have B is equal to C, for B is equal to C, all right? It's not like B colon equals C, right? B is equal to C now is a bit different because they are making a statement of assertion. I'm asserting that C is exactly equal to B. All right? So basically, this is how we update. Theta I in every step that we take. All right. So this is how we update theta I in every step that we take. In every step taken in the gradient of So now this is an algorithm that will govern that. Okay. Let's say for an example, we have only one training example. So in other words, for an example, m is equal to 1. Alright? Say for an example, m is equal to 1. Then how would we then, say for an example, m is equal to 1, therefore it means that the partial derivative of j of naught, j of theta, the partial derivative of j of theta must be given by the partial derivative of j of theta, which is expressed as that. So now this is how we would write this would now be the way of writing the derivative. Alright? If I could just release here. Okay. Just remove the formula. Alright. So basically that's the derivative. Alright. So but now if we can perform the operation on the right hand side, we'll get that this now this derivative, partial derivative actually of j of theta with respect to theta I would be now equal to, so we'll take the 2, we'll bring it to the front there. It will be 2 multiplied by a half into the estimated price minus the actual price. So basically we're taking a 1 there. Then you multiply, this will be now multiplied by the derivative with respect to theta I of the difference between the estimated price and the actual price. Alright? So this will be expressed in this particular manner. Right? Let me just rewrite what I have there so it can be clear. Right? Let me just rewrite what I have here so it can be clear. So we've got an expression like that for the derivative. So now this obviously is given as the estimated price minus the actual price. Now look at that step. Look at the partial derivative of the difference between the estimated price and the actual price with respect to theta I. Right? I just want you to take note that h of x, this is our hypothesis, and remember that we've actually defined our hypothesis in the previous lecture. We've defined the hypothesis to be the sum of these so we actually define the hypothesis to be that. So note that all of these terms in the sum don't depend. So all of these terms in this sum, All of the terms don't depend on theta I. They don't depend on theta I. All of these terms in the sum, they don't depend on theta I, except for one term, right? Except for one term, except for this term, right? Theta I, xi. It's only one term that actually depends on theta I in the sum. Therefore, this now can be given as the difference in the estimated price and the actual price. And when we take the derivative of that, this will give us this. Alright. So now what we need to do now this is the partial derivative of j of theta with respect to theta I. Now it is given as that. So we need to go back and update our equation and update our algorithm. Alright? It is given as that. So I just have to erase the board. Erase the board. It is given as that. So now we know that our algorithm minus alpha cross minus alpha so now this will be I minus alpha. So now we've already got that expression that is equal to the difference between xi. Alright. So now this is an algorithm known as the gradient of steepest descent. Alright. That is this is the learning rule, right? So this is what the machine will use. And remember that in this algorithm, remember that alpha here is the learning rate. The learning rate is alpha. This alpha, it actually tells us how big or how large, in fact, or how small do we take the steps towards the steepest gradient descent. All right. Now, if alpha is too small, right? If alpha is too small, in other words, if now you choose this alpha to be too small, you'll be taking small steps towards the minimum, towards the steepest descent, right? Towards the gradient's steepest descent, right? You take very small steps. And what we will do eventually, you will take a longer time to get to the minimum. Just like if you choose alpha to be very big or too large, in other words, you'll be taking too large steps to go towards to converge, in other words, towards the minimum. Then you might end up overshooting the minimum. All right. The function j of theta in two-dimensional plane has got only one local minimum. Okay, only one local minimum. Basically, the idea of the gradient steepest descent is to repeatedly take steps, all right, until you converge to the local minimum. All right. Bear in mind that the local minimum and the minimum that the gradient is definitely equal to 0. So what happens as we approach this local minimum? What happens from a certain point, and as we approach this local minimum, what happens? We're approaching this local minimum. What happens is that the gradient keeps getting smaller and smaller and smaller and smaller. Think about it. All right? Think about it. Even here in this egg container, you can see that it's a curve. It starts to get curvy. You see the gradient is steeper. As I'm approaching the minimum, the gradient becomes so small. It becomes smaller and smaller. All right. So basically, this is an algorithm that I wanted us to be able to prove today. All right. And in our next lecture, lecture number 4. In lecture number 4, we're going to be continuing with the gradient of steepest descent, but now we're going to look at the example where we have training examples that are greater than 1. In other words, we have many number of training examples. All right, where we would take another expression of theta of I. All right. Basically, the next topic is batch gradient descent. So stay tuned for the next lecture on batch gradient descent. All right. So we're going to be focusing on batch gradient descent. Thank you very much, ladies and gentlemen, for tuning in on to this lecture. I myself, Vuyo Sileku, thank you so much. There is no other life besides this for myself. I present these topics absolutely to you guys with an understanding that you really need further narration regarding machine learning. Thanks a lot. Just to recap, today we were touching on gradient descent as one of our search algorithms. So we came up with an expression for theta. Okay. Thank you very much. This is the way of minimizing J of theta. Stay tuned for our next lesson when we will be doing batch